Before we go over projectile motion, I want you to consider the following problem. We have a bullet being shot from a gun at the same instant that another bullet is dropped from the exact same height. I want you to consider which bullet will hit the ground first, the dropped bullet, the fired bullet, or will they hit the ground simultaneously? And enter your answer in the box that appears. Well, hopefully you figured out that they will in fact hit the ground simultaneously, because both will fall under the influence of gravity from the exact same height, and therefore they will hit the ground simultaneously. The only difference is the fired bullet will move horizontally while falling vertically, and they won't land in the same place, but they will land simultaneously. Now, when it comes to projectiles, which is what the bullet was, we're going to emphasize a few key points about projectile motion. Projectiles are just objects that are launched in free fall, but at an angle. So their initial velocity is not straight up or straight down, but at some sort of an angle, so it has a vector with both vertical and horizontal components. And the key points are that first, the vertical and the horizontal motions will be independent of each other. The horizontal motion will just be constant velocity, while the vertical will be constant acceleration. In fact, it'll be free fall. So that the x component of the acceleration will be 0, while the y component will be minus g, or minus 9.8. Beyond that, the objects will just follow the same kinematics that we have been doing, where the initial velocity will just be the two components of the initial velocity vector. And in fact, we can use essentially the same equations we've been using for constant acceleration. Here, we've just basically replaced everything with vectors. So the position vector is the initial position, which is a vector, plus the initial velocity, again a vector, times time, plus 1/2 a, which will be another vector, times t squared. And the velocity will change constantly, so the velocity at some given time will be the initial velocity plus the acceleration times time. And this was the third kinematic equation, which just uses the velocity squared. The one thing is the quantities are all vectors. The initial position is the initial x and the initial y. The initial velocity, again, is a vector. And the acceleration will only have one component, which will be the y component, and that'll be at minus g. Notice here we're using the unit vectors I and j to represent x and y. Now, to see the first key point, which is that horizontal and vertical motion are independent of each other, and one is constant velocity and the other is constant acceleration, we're going to show a video of two balls. One will be falling straight down while the other one is being launched horizontally at the same time at the same height. So here we see the two balls. One is falling straight down while the other is moving horizontally. And notice this is exactly the same as the little question we started out with, and they hit the ground simultaneously. Only difference being this one lands over here. Now you will notice that as they are falling, we're going to have little lines crossing them horizontally and vertically as the two fall. And you can see they're always at the same vertical height. So the fallen ball and the projected ball are both at the exact same vertical height. The only difference is that the projected ball, notice, will be moving across the screen. And notice these are the positions that it was, and they're all equally spaced horizontally. So we have constant velocity in this direction, the horizontal direction, because all of these lines are evenly spaced. And in this direction, we have constant acceleration. Notice they are close together when it first started falling and much farther apart at the end when it hit the ground. So this is accelerated motion, and this is constant velocity. We can see this in another way by looking at a little model of projectile motion. Here there are basically ping pong balls that have been simply attached to a plexiglass at the positions equally spaced in time.
Here you see the vertical component of a projectile's motion.
What I want you to do here is answer the question as to how do we know that this is in fact constant acceleration?
Here you see the horizontal component of a projectile's motion.
And again, I want you to answer a question as to how do we know this is constant velocity from what we can see. Now, in this next video, what we're going to see is an airplane right here that's going to drop a flare. The airplane will continue flying at a constant velocity at more or less the same altitude while the flare is dropped. And there it goes. And you will notice the flare is always more or less directly underneath the airplane as it falls down and eventually hits the ground right here. So what we're going to do first is back the video up to when the flare just hits the ground or the water. And right there it hits the water. And we can see that this is a vertical line, and it's almost directly underneath the airplane. It's not exactly under the airplane due to the effects of air resistance. So from the airplane's perspective, all the pilot would see is the flare more or less dropping straight down directly below him. From our perspective on the ground, we see it moving horizontally while falling vertically. And this tells us why the two motions have to be independent of each other, because we're watching the same object fall from two different perspectives. From the perspective of the airplane, all he sees is free fall, it falling directly beneath him. We must see the exact same thing if we're watching it from the side. We must also see vertical acceleration. And because the flare is always directly underneath the airplane, the flare must be moving horizontally at more or less the same speed as the airplane. And therefore, it must be moving at a constant velocity, just like the airplane. So the horizontal motion is constant velocity, and the vertical motion is constant acceleration. Both observers do have to agree on that. What I then did was did a frame-by-frame video analysis of the airplane and the flare, and the results are shown right here. The airplane and the flare both had more or less the exact same velocity. The horizontal velocity of the flare turned out to be the slope of this red line right here, which is the horizontal position of the flare as a function of time. That slope ends up being 27.3 meters per second. The green one right here is the airplane, and notice it's almost exactly on top of the flare, moving at almost exactly the same rate. Turns out it's a little bit faster. It's 29.4 meters per second. They agree to within 7%. Here we can see in the blue, that is the vertical position, which is parabolic. And I then graph the velocity right here. It's very noisy because of the quality of the video is not that great. But the slope of this line turns out to be 10.4 meters per second squared, which is within 6% of the accepted value of 9.8. So this is constant acceleration downward while it is moving at constant velocity and essentially the same velocity as the airplane. The last video we're going to watch shows something similar, only now we're going to launch a flare from a moving snowmobile. And notice the flare is always directly above the snowmobile and lands right next to it. So from the perspective of someone in the snowmobile, they would just see the flare go straight up and then come straight back down, landing right next to where it was launched. We see it moving horizontally while also falling vertically, showing we see horizontal constant velocity with vertical constant acceleration. Now what we're going to do is some examples based on the mathematics. And first thing we're going to look at is something, a projectile launched from the ground. We'll make it a soccer ball, kicked with an initial velocity of 24 meters per second. And it will be launched at an angle of 40 degrees above the horizontal. So this angle right here will be 40 degrees. What we want to do is find out how long is the ball in the air, how far does it travel horizontally, or what is this distance right here from where it was kicked to where it hits the ground, what is the maximum height that it attained, which is this height right here, and what is its velocity when it hits the ground back over here. Well, for the first part, we're going to separate the velocity into its x and y components. The velocity vector is 24 meters per second at an angle of 40 degrees, so we can calculate the x component using the cosine of 40 and the y component using the sine. So this gives us the two components. What determines the time in the air is the vertical motion. So what we're going to use is this velocity, the vertical velocity, the 15.4 meters per second. We want to find a kinematics equation that includes time, and since our criterion is when is it on the ground, and it starts on the ground, we want to use the first of the kinematics equations. The ending position and the starting position will both be 0. It's going to start and end on the ground. This velocity is the vertical component of the velocity, which is the 15.4 meters per second. And once we define this to be up, we have to define the acceleration to be minus g, or minus 9.8, to keep our plus and minus signs consistent. So this is minus 9.8. We plug all these numbers in and solve the resulting equation for t, and we'll find that t is 3.15 seconds. So that's how long the ball is in the air. Now that's how long it takes for the position to go from 0 back down to 0. Then we want to find out how far does it move horizontally. Well, to do that, we notice in the horizontal direction, it's moving at a constant velocity. In fact, it's this constant 18.4 meters per second. And it's moving at 18.4 meters per second for however long it's in the air, which is 3.15 seconds. Multiply those two numbers together, and we find out how far it moves. Then we want to find the maximum height. Well, the maximum height is where the vertical component of the velocity goes to 0. And since here we want to find the height and don't care when it is at that maximum height, we want to use an equation that does not include time because we don't formally know when that happens. But we do know where, we don't want to find out where that happens. So we're going to use the third of the kinematics equation, which has the velocity squared. We want to find out where this velocity goes to 0. So we're going to set that equal to 0. That defines the maximum height. This is our initial velocity, the 15.4 meters per second up. And again, once we define this as positive, this right here must be a minus g, a minus 9.8. And delta x is how high it goes, and since it starts on the ground, delta x will give us our maximum height. Plug the relevant numbers in there, and we find the maximum height is 12.1 meters. Finally, we want to find out the final velocity. Well, it's got two components. The horizontal component is constant, so that's the initial 18.4 meters per second. The final one, well, all it's going to do is reverse direction, because it's going to be accelerating upward at minus 9.8, and slow down and stop, and then fall back down the exact same distance, and it'll pick up the exact same velocity that it lost. Or all that's going to happen vertically is that this velocity is simply going to switch from being up to being down. So it'll have the same magnitude of the velocity, but just the opposite direction at minus 40 degrees. Now we're going to consider a second example. In this example, we're going to put a projectile up at the top of a cliff. So it's not going to start and end on the ground. It's going to start 48 meters up in the air at the top of a cliff. And we're going to shoot it at an angle of 30 degrees with a speed of 120 meters per second. We're going to look for the exact same three quantities: the time, the distance traveled, the height it reaches, notice above the ground, not above the cliff, above the ground, and its velocity upon impact. First, we're going to separate the velocity into its two components. Same thing as we did before, using the sines and the cosines, and we get the two components. Time, again, comes from the vertical motion, using the exact same equation. The only difference is, while the final position is 0, the initial position is not. It's at 40 meters. Everything else we plug in the exact same way. The difference is now we have a quadratic equation, because this term is not 0. We get two solutions. One is positive and one is negative. Well, our interpretation is, well, obviously the projectile must land after it was launched, so we're looking for the positive solution. Because t equal to 0 is when it was launched, negative solution is before it was launched, and the positive are after it was launched. So we want to find the positive solution. And again, the horizontal distance traveled is just the horizontal velocity times the time it's in the air, in this case 1.34 kilometers. Maximum height is again determined by when the vertical velocity goes to 0, Again, we solve it the exact same way as we did before. This final velocity must be 0. Initial velocity is this vertical velocity. And again, we have minus 9.8. We solve for the height. Notice this is the height above the cliff. That's what this delta x would be, the height above the cliff. To get the total height, we have to add the height of the cliff. So we must add this 184 to the 40 to get the total height above the ground. Now to find the final velocity, Vx is constant, so it's the same as it was at the start. The final will change. It'll be the initial minus g times the time it's in the air. Time is in the air we already found. That was the approximately 12 seconds. Plug this in and we find out the final velocity is about minus 66.2 meters per second. To find the magnitude and direction, here's our x component. Here is our y component. Pythagoras gives us the magnitude of the hypotenuse, and a little bit of trigonometry gives us this angle.